Today we're going to look at Kepler's laws of planetary motion. A little bit of historical context. Kepler was doing his work around the same time as people like Galileo, and Tycho Brahe is another famous guy. Tycho Brahe was Kepler's teacher, I guess. Kepler was his apprentice for a while. And most of the other astronomers of the day, even there were arguments going on about whether the Earth was the center of the solar system or the Sun was the center of the solar system. But pretty much everybody other than Kepler insisted that planetary orbits involved circles. In order to fit with data that, if this is the Sun, for the orbits to be circles, either around the Sun or around the Earth, depending on who you're talking to, the planet had to follow a circular path, but then rotate around a circle within a circle, creating this kind of spirally path through the Earth. So it was pretty complicated. But everyone was sure that circles were the perfect shape, and therefore planetary motion, the orbits must be circular. Tycho Brahe, who is Kepler's teacher, was proposed a kind of hybrid model where the Earth orbited around the Sun, but then everything else, the Sun orbited around the Earth, and then everything else orbited around the Sun. But eventually, people arrived at the conclusion that of a heliocentric system, that the Sun is at the center of the solar system. Kepler was a heliocentrist, but he was the first guy to depart from the idea that circles are the shape of the planetary orbits. Kepler said that planetary orbits follow elliptical paths. Circles are ellipses, orbits are ellipses, not circles. A circle is an ellipse, so you can have circular orbits. However, the planetary orbits are not circular; they're actually elliptical, and this had the advantage of simplicity, because rather than having these sort of spirally paths, Kepler was able to just draw these elliptical orbits for the planets, and those were able to accurately predict the locations of the various planets. Kepler was working with Tycho Brahe's data. Tycho Brahe took extremely detailed measurements of all the locations of planets in the sky at different times of year and all that, and Kepler, extrapolating from his data, produced his three laws. Now, planetary orbits are elliptical. Now, this might give you the idea of a shape kind of like this. However, the planetary orbits are very, very close to being circular. So, if I accurately drew a planetary orbit on the paper, you might not really be able to tell that it wasn't a circle, except for maybe Pluto. Pluto isn't technically a planet anymore. Pluto's orbit is more of an elongated ellipse. For example, Venus has a difference of 1.36% between its closest distance to Earth, or to the Sun, and its farthest distance from the Sun. Those are known as perihelion and aphelion. Para means closest, helio, Sun. So perihelion is the point in the orbit that's closest to the Sun. Aphelion is the point in the orbit that is farthest from the Sun. Remember those prefixes. There are different endings that you can tack on there. If you have an orbit around Earth, you can say perigee, apogee. Or any general orbit, you can say periapsis or apoapsis. Later on, Newton, with his work on universal gravitation, expanded on Kepler's first law, that objects moving in the vicinity of a star follow conic paths. So orbits can be circular or elliptical. Well, and again, a circle is an ellipse, so orbits can be elliptical, but objects that do not remain in orbit can follow hyperbolic or parabolic paths through the solar system. So if you get a comet or an asteroid of some kind that happens to float through the solar system near the Sun, it will follow a conic path and then go off into forever. Kepler's second law, that's Kepler's first law, orbits or ellipses. Kepler's second law, given planet will sweep out equal area and equal time intervals. This is difficult to understand without looking at a diagram. So if we've got the sun right here and we've got a planet, an annealed planet, let's just whatever planet this is, and it's got its path around the sun. Say it takes from here to here. This is a time interval delta t, and when I say sweep out, it's referring to the area of this sector is the term for it. The area of this sector is what this area is talking about. So this is some time interval t, the area of this sector. I'll say in some other time interval, say this is the same time interval. This is area 1, this is area 2. Kepler's second law says that if this time interval is the same, those two areas are equal. It doesn't matter how close or how far away you are at either point. The areas swept out are going to be equal, and it took some pretty detailed calculations to work that out. So why does that happen? Well, the reasons for that have to do with conservation of energy and conservation of angular momentum. Energy we'll talk about later in this unit. Angular momentum we'll talk about later in the semester. So now the question is, when is Earth moving the fastest? Well, if we look back at our diagram, we know that if you're when you're farthest from the sun, the distance between the sun and the planet is going to be greater, of course. So if the planet moved the same amount of distance in this time, you would get a bigger area. But that doesn't happen. You have the same area, which means that when we're farther away, the planet moves more slowly. When you're closer to the sun, the planet moves more quickly. So when is Earth moving the fastest? That would be at its perihelion, which is actually I believe it's at the winter solstice for the northern hemisphere. So you may have heard this before, that the Earth is actually closer to the sun in the winter than it is in the summer, which is true for the northern hemisphere. In the southern hemisphere, it's closer in the summer and farther away in the winter. The distance to the sun is not the reason for the seasons. That has to do with how direct the sun's rays are due to the tilt of the Earth's axis. So you can look at this. So during a time period immediately after its aphelion, Venus sweeps out an area of 0.0305. Oh, I wanted to mention this, AUs. AU stands for astronomical unit. Astronomical units. 1 AU is defined to be the orbital radius of Earth, how far the Earth is from the sun on average. And you can look, if you want to know what that is in meters, you can look it up on Google or on the inside cover of your textbook. I think it's something times 10 to the 11th meters. Anyway, so just like meters squared, an AU squared is a unit of area. So during a time period t immediately after aphelion, Venus sweeps out an area of 0.0305 AU squared. How much area does it sweep out during time 2t, just before perihelion? Well, we know Kepler's second law, equal area equals equal time. So during any time period t, we sweep out an area of 0.0305 AU squared. So time 2t, how much area do we sweep out? Well, we just double that. So 0.0610 astronomical units squared. So that is Kepler's second law. Kepler's third law is something that you have all the tools to derive. So if you've got a planet in a circular orbit, what's providing the centripetal acceleration or centripetal force? Well, the only force acting on a planet in orbit is gravity. That's gravitation. So Newton's second law for this case, sum of the force equals ma. Well, what force do we have? Just gravitation. G, mass of, well, a lot of times we use this sort of notation, big M, little m. Big M being the sun in the case of planets, or big M just being the more massive object, the one that's being orbited, and little m being the one that's orbiting. So the force is g times the product of the masses over radius squared. Mass times acceleration. This is since it's circular motion, acceleration is centripetal acceleration, v squared over r. So we can do some canceling. Mass cancels out. One factor of radius cancels out. And Kepler's law relates the period to radius. We've got velocity instead. So remember, if we're in a circle, velocity is 2 pi r over the period. So then putting those together, we're left with gm over r equals v squared, so 4 pi squared r squared over period squared. And so if we cross multiply, we've got period squared times g times mass equals 4 pi squared r cubed. And then solving for period, we've got period squared equals 4 pi squared r cubed over gm, or period equals, take a square root of 4 pi squared is 2 pi. Remember, square root is a 1/2 power, so r to the third to the 1/2 is r to the 3/2 over square root gm. That's an equation we can use. What Kepler actually stated in his third law is that the square of a planet's orbital period is proportional to its orbital radius cubed. So Kepler did not get this specific equation. This specific equation came from Newton. What Kepler said is that period squared is proportional to radius cubed. He did not work out that it was proportional by this factor of 4 pi squared over gm. That was Newton's work, and now your work, or mine, I guess, because we have derived where that comes from.